We start? Okay, great. Okay, let's go ahead and get started. So the main topic for today are sort of generalizing our connection between random walks on graphs and spectral expansion that Dinur covered to high-dimensional expanders. In particular, understanding what are random walks on hypergraphs, on high-dimensional expanders. What are they useful for? Do we have similar connections with mixing time? And hopefully at the end, we'll see both what they're useful for in terms of mixing and also some of the ways that these are applied in the study of local testability and PCPs. A little snapshot of that part. Okay, so we saw this fundamental connection between lambda2 and the mixing time of the underlying random walk on a graph. So there's, of course, a natural question, which is, is there a high-dimensional analog of expansion implying mixing? Okay, so this question, as far as I know, within the HDX community, was first studied by Kaufman and Mass. And we'll talk a little bit more about the motivations in these things later. But okay, so what's the natural generalization of a random walk on a graph to a random walk on a hypergraph? There are sort of any number of variants that you could look at. So I want to try to argue there's a particularly natural set of high-dimensional walks to look at on these complexes. So the first thing I want to do is look back at this simplicial complex diagram we had last time. And I want you for now to just completely ignore the top layer. Only look at x2 and x1, which is a graph, right? This is the underlying graph of the complex. For now, that doesn't matter. I'm just thinking about it as a graph. I'm just reusing the diagram. Ignore x3. So in particular, what does this graph look like? This is just the complete graph on 4 vertices, right? So this is K4. Just quickly. Let's say we have vertices 1, 2, 3, 4. Okay, and what does the standard random walk look like on K4? I want to sort of map it to what it looks like on this simplicial diagram over here. So I'm going to change things a little bit, and I'm going to consider the lazy random walk instead of the normal non-lazy random walk we discussed before. What does this mean? Is orange visible? Is that visible to people or no? Good? Okay, I'm hearing good.
Indistinguishable.
It's indistinguishable from white. Okay. Is there a known color that is distinguishable from white on these boards? Okay. You know what? I'm just going to do that. Is that more distinguishable? All right. Well, it doesn't really matter. Okay. I start at some vertex, and the normal random walk, I'd move to a random neighbor, right? In this case, all of the things are connected, so I'd randomly pick 2, 3, or 4. In the lazy random walk, what I'm going to do is, what does it mean to pick a neighbor? Really, I'm picking an edge, right? I'm starting at 1. I'm looking at all of its edges. I'm moving, say I wanted to move to 3. I'd really be picking the edge going between 1 and 3, and then I would sort of be moving from that edge back to 3. In the lazy random walk, I start by looking at 1. I pick one of these random edges, and then each with probability 1/2. I either go to 3 or I go back to 1 with half probability. So what does this look like on this diagram over here? Again, ignore x3. I start at 1. And what does it mean to walk to an edge? I take a step up in this diagram, right? Vertices, edges, triangles will come into the picture later. So I walked from 1 to 3. So here's 1, 3 in this diagram. So I took a step up. I picked a random neighbor in the level above in this inclusion diagram. And then I picked a uniformly random element of 1 or 3, which is moving back down in the diagram. So I chose 3, but I might have chosen 1 with half probability. But for the sake of making it more interesting, let's say I chose 3. So does anyone have a natural suggestion of how now to generalize this if x3 is in the picture? What's a natural high order analog of this random walk? Yeah, so there's great. So this is a random walk that's sort of on the vertices that I've shown you right now of this complex, but I could apply exactly the same procedure starting from an edge of this complex, right? So I could start, trying to erase the orange. I could start from 1, 3, ignoring this now, and now I could pick a random, 3 set, a random triangle that contains 1, 3, say 1, 2, 3. So I move a step up, and now I'll pick a random pair from within 1, 2, 3 and move back down to that edge, right? So let's say I pick 2, 3. So this gives me a natural corresponding random walk on the edges of the complex. And of course, I could, there was nothing special about edges or vertices. I can define this at any level of the complex. This is called the up-down walk. I first take a step up, I then take a step down. Pretty clear? Maybe it's worth drawing. Just like I said, it doesn't matter what level of the complex you're at. I'm not going to draw all the edges here, but I could be on a d-dimensional complex, and there's always, between any level I and let's say I plus 1, I can always do this walk where I sort of just move up, down. So we're going to denote this random walk as p wedge, p up, down, and then index I for the level that the walk is being performed on. Okay, any other suggestions for natural walk? Yeah. Good. Here's another natural. I'm going to get to these later, and actually we're going to prove a spectral bound for exactly those walks. Yeah, so here's another thing. I could move from I. There's nothing stopping me from going to I plus 2. So I could move up 2 steps and then move down. Okay, so this will be I to I plus 2. Okay, good. You could also move down. So these are all variants of the walks that are actually very important and that we're going to consider. This gives us sort of this set of random walks on the simplicial complex. So I guess let me be clear. The suggestion was instead of going up 1 and then down 1, you could also go down 1 and then up 1, or on this diagram, right, we would start at 1, 2, 4 and walk down to 2, 4 and then walk up to 2, 3, 4, for instance. So this gives this basic set of random walks. Yeah. Good. So what does it mean? These end up being the same, basically. What does it mean to go to I plus 2? I'm going to add 1 vertex and then add 1 other vertex. If you want to do, I'll do this a little bit more formally in a bit, but really what is happening here, I have some I set. Conditioned on the I set, I'm sampling a new vertex. I'm adding 1 more vertex, and then conditioned on this, I add 1 more vertex. Because of all these things about conditional distributions, it's exactly the same as just adding a pair of vertices. So we'll actually define these longer walks just to be the composition of the single step walks. But yeah, you're free to think of it either way, jumping, or usually it's useful because we'll sort of do inductive arguments on the length of these, of thinking about it one by one, but it doesn't really matter at the end of the day. Yeah. Yeah, so I'm cheating here. Here, everything's uniform because it's actually the complete complex. And I will define things formally, and we'll use the correct conditional distribution. Yeah, indeed, like I was saying before, generally when you walk down, things are uniform. Because you remember how we generated these distributions on the complex. We sample from here, and then we uniformly at random subsample. So when we walk down, things will be uniformly random. But when we walk up, it needs to be from the correct conditional distribution, like we talked about last time. And I'll formalize that in a bit, but I just wanted to sort of set things up morally first, because these are really very simple objects. Yes, you have to look at the exact probability of moving to different places, but you're just moving up a step and down a step, right? These are very, very easy and fundamental objects. Okay, so why should you care about these? I mean, mathematically, it's very natural to say we had this random walk mixing theorem on expanders. Let's see if we can prove it for some natural high-order analog. But it turns out that beyond this, there are some incredibly good motivations to study these random walks. In particular, there are at least 2 that I know of. If anybody else in the audience has more, I'm happy to hear them. One, I still have orange. So the motivation of studying these of Kaufman and Mass was actually towards PCPs. So the connection of mixing of random walks and spectral expansion in graphs, edge expansion, et cetera, was used in this proof of Dinur of the PCP theorem. And Kaufman and Mass thought maybe there's some sort of connection we can push to lower soundness by going to high dimensions. Maybe these sort of high order random walks will be important. So one, toward better PCPs. I haven't told you what a PCP is. It's some hardness amplification or hardness of approximation thing. We're not going to go into it, but I'll talk a little bit about how these things are, in fact, related to this. And probably most of you know this was actually realized. It took like 8 or 9 years, but there's a breakthrough series of works starting after Kaufman and Mass with Dinur and Kaufman, then maybe Kaufman Gottlieb. There are so many of these papers. Dikshin Dinur 23, Bafna Minzer 23, Dikshin Dinur Lubatsky 23, 24. Does anyone know? One of those years. Bafna Minzer Lifshitz 24, and then finally the actual PCP constructions coming out of all of these things is Bafna Minzer Voss Yoon 25. Think. Okay, anyway, just to give credit where credit is due, this, after some long line of work, of course, there are many, many more things than you need than just these random walks, but they really do play a core role in this type of analysis. We'll talk a little bit about it. Sort of incredibly, this is not the only breakthrough that has come from these random walks, even though it was the initial motivation. In fact, much more quickly than we got to realizing this, it was realized, I guess, initially by Inari, Lou, Ovis-Karan, and Cynthia Vincent, that these random walks, in particular this down-up walk that starts at the top level of the complex, removes a vertex uniformly at random, and resamples, is actually a generalization of a very well-studied set of Markov chains in TCS and statistical physics called the single-site Glauber dynamics. We're not going to deeply go into this, but I am going to show you why this is an incredibly natural set of chains, how it shows up in fundamental places in TCS, and how we can use this theory to prove random walk, to prove mixing bounds on many systems that we didn't know how to prove mixing for before. In particular, matroids. We'll just cover spanning trees today, but in the exercises, you'll actually prove fast mixing for matroid bases, which is equivalent to what's called the Mihail-Balzerani conjecture, and was open for 30 or 40 years before it was resolved through this random walk machinery. So second is fast mixing of high-dimensional systems. I think it was, maybe this was not surprising to people who had worked on these systems before, but to me it was very surprising that so many of these combinatorial systems, independent sets, spanning trees, icing models, for people who know this sort of thing in statistical physics, they all end up being high-dimensional expanders. And you get, through this local to global theory that we're going to cover, you immediately get fast mixing bounds for these systems. Okay, so now I actually want to look at what this random walk looks like a little bit more explicitly on 2 examples. In particular, I want to start with the hypercube. Hopefully this is going to be something you're all familiar with. So again, sort of a motivation, we like to think of high-dimensional expanders as sort of generalizing product spaces or independent variables. So I basically want to, we'll look at the hypercube, we'll look at its properties, and then basically our goal is going to be generalize these properties to this much broader set of simplicial complexes. Okay, so this board is okay. Okay, so we talked briefly about the hypercube convex last time. I'm going to be a little bit more formal about it this time. Last time, I think I just drew this picture, that it was sort of the complete partite, the complete complex on D parts and 2 vertices per part. So you had a 0 or a 1 in each of these D coordinates or bits, right? So this was sort of standing for 0, 1 to the D. Let me be a little bit more explicit about it. So this is a complex whose vertices are the space 0, 1 cross D. Right? So this is corresponding to which coordinate you are, and this is which binary bit you're taking. And then the top level of faces, XD, This is all strings x11 up to xd d, right? So one of each coordinate, such that the tuple x1 through xd is in the hypercube. Okay. I know it's a bit weird to express this as a simplicial complex, but I want you to see what the random walk we've just set up on simplicial complexes looks like on this basic example. Any questions about this this particular simplicial complex? Like why is this the hypercube? Is that clear to people? Okay, so if it's clear, somebody tell me what is the down-up walk on this complex. In particular, starting at level D, what is this random walk? Sorry, thank you. Yeah. So whenever I forget to write a distribution, it's because it's uniform. Thank you. Uniform distribution. Actually, you could pick any product distribution, and this will end up basically being the same here. But let's assume things are uniform. So every coordinate is one or zero with probability a half independently across all the coordinates. Thanks. That will basically be the stationary distribution of this process. Okay, so what is the down-up walk? Let's say I start at a face x11 to xd d. How does the down-up walk operate on this? Pick one of the coordinates randomly. Good. Yeah, just choose 0 or 1. So this is just a hypercube graph, right? This is like two strings are connected if they differ in one place, but it's a lazy version of this. So it's also has half connection to itself. So this is just a lazy hypercube graph. Hopefully all of you have seen this come up in various places. It's common to the first time you analyze mixing to look at the hypercube. This type of walk is really fundamental in understanding Fourier analysis and influence, and if you've done Boolean function analysis, it's everywhere in TCS. So the fact that we are going to be able to generalize its properties to much broader objects turns out to be extremely powerful that you can do this. Okay, so now let's see a non-product. I'll mention, I could also have taken this to be, I could have taken these parts to be as big as I want. There's no particular reason it was 0 or 1, just that's sort of the easiest setting. Okay, so let's look at spanning trees. Right? This was our other example last time. Okay, now I'm going to be less careful and not write out the complex and just draw the object on the board. Let's take our graph to be K4. I think last time I drew something crazy and it was just confusing. Okay, so now our graph is simpler. And let's say we start at some particular spanning tree. Sorry? There's one more. This. Good point. Okay, so this is a starting spanning tree. What's the down-up walk? Somebody tell me. Shouldn't be hard. Pick one randomly. Place it with just a normal edge. And then add another edge, condition on it giving you a spanning tree. So maybe we add this guy in. Okay, so it's a very simple process, right? I look at the set that I have, I remove one guy at random, and I add one back in conditional on being in the top level or from the correct conditional distribution. Okay. So what do we know about the mixing of these random walks? Right, so what we'd like to show is that if I start at, say, an arbitrary spanning tree, after I do this sum, if I have a graph on d vertices, the number of spanning trees could be something like d to the theta d. There are exponentially many possible spanning trees. Nevertheless, we'd like this random walk to mix in polynomial time. Right? We'd like to use this as a procedure to, say, sample a random spanning tree in a graph by just starting at something that's arbitrary, doing this down-up walk process, maybe d or d squared times, and then saying, okay, we can prove that this is close to a uniformly random spanning tree. And okay, maybe for spanning trees, this is really well studied. There are other ways to do this, but we'd like to do this in a way that generalizes to objects like matroid bases, which generalize spanning trees or other types of systems. Okay, so what can we actually hope to prove? I want to go back to the hypercube complex. How many steps does it take for this random walk to mix? I start at an arbitrary string. How many times do I need to apply the down-up walk until, I don't know, with 99% probability or something like this, I'll be at a completely uniform random string? Yeah, I think I'm using d instead of n, d log d. Yeah, exactly. Why? Yep. Roughly d log d. Actually, like, we have some sort of cutoff, so it's like d log d over 2 very specifically. But it's very fast, right? We just have to resample each coordinate one time, and because everything is independent, by the coupon collector bounds, this takes about d log d steps to sample everything with high probability. So, okay, maybe a very strong goal would be to prove that this actually mixes in O of d log d steps. That's a little lofty of a goal. That would be very, very fast. And I will actually mention how you can prove this using similar machinery that we're going to develop. But let's start with something a little bit more modest, which is just trying to prove a spectral bound on this walk. Right? Madhur showed how if you have a bound on lambda 2, it automatically implies an upper bound on the mixing time. It's not going to be as good as d log d. Even the upper bound you get on the hypercube would not be this good. So let's see again what you get on the hypercube. Yeah. Oh, so when I resample a coordinate, I'm flipping a coin, right? So once I've resampled every coordinate, there's no correlation with where I started. Everything has just been completely independently replaced. And then it's just how many times, all I'm doing is picking a random coordinate, and I'm just solving the problem. How many steps does it take to pick every coordinate out of D? And that's the coupon collector problem, yeah. So, over here in spanning trees, things get tricky because the coordinates are correlated. Well, there aren't really coordinates, but things are correlated, right? So I can't just say if I've sort of replaced every edge of my starting spanning tree, which would be the analog, I can't say I've mixed because there are correlations between all these coordinates. So the question is there some way to generalize? That was a very specific analysis to independent things, but we know that spanning trees sort of act independent in some spectral way, right? They're high-dimensional expanders, or at least maybe if you did that exercise, you know that they're zero-local spectral expanders. Right. Yeah. Exactly. The correlations are right. You can't pick everything in a cycle, so it's relatively weak correlations, which is why we will be able to generalize this. Okay, but so what we're going to prove is a spectral bound on this walk. Right? So in particular, for the hypercube, very basic spectral graph theory or Fourier analysis tells us that the second eigenvalue of the down-up walk is 1 minus 1 over d. This is just coming from looking at the characters, right? This is a Cayley graph on f2 to the d, and I just look at the characters, which are the eigenvectors, and I directly compute that this is the eigenvalue. If you haven't seen this before, it's a good exercise to do. I'm not going to go through it, but this is sort of our goal. Right? If the hypercube has this 1 minus 1 over d value, what we would like to prove is that high-dimensional expanders, maybe even zero-local spectral expanders, will get exactly 1 minus 1 over d, or maybe we'll get something close to this, but decaying with how strong the expansion is. Right? This is sort of our goal now. We'd like to achieve this, and let me just remind people the connection that Madhur showed with mixing time. Yeah. Yes, this is the eigenvalues of the transition matrix of this one. Yeah, the like appropriately weighted. In this case, things are uniform, so I guess that the weights are easy. But in general, things won't be uniform. So it's and I'll be more careful in 5 minutes about how these are defined. These are indeed the transition matrix of these walks. We saw that this implies a mixing time bound of I think maybe Madhur actually wrote log of 1 over lambda 2, but when lambda 2 is close to 1, this is roughly the same as 1 minus sorry, 1 over 1 minus lambda 2, which is the relaxation time or inverse spectral gap, which in our case is just d, right? So this is d times log 1 over epsilon times 1 over the smallest probability in the support, which in this case there are 2 to the d possible strings. So this is 1 over 2 to the d. So this is roughly, sorry, spanning, no, this is the cube, yeah. So this is roughly d squared, right, that it would get us. And if we did the same calculation with spanning trees, say we did manage to prove that spanning trees in fact have, are upper bounded by 1 minus 1 over d, then how many spanning trees are there? At most d to the d, right? So we'd get roughly d squared log d bound on mixing time. So that's going to be our goal for the rest of the lecture. And let me just note again that, okay, maybe we already had better algorithms for spanning trees in particular, or already knew that the gap was at least 1 minus 1 over d, but it was open for 30 or 40 years to extend this to matroid bases, to prove in particular this 1 minus 1 over d bound is equivalent to a conjecture of Mihail and Vazirani about the edge expansion of bases of matroids. Again, this is defined more in the exercises if you're curious about it. So the fact that if we can prove this for 0 local spectral expanders, for instance, since you'll prove matroids are 0 local spectral expanders, sorry, this would resolve the Mihail-Vazirani conjecture. And this is done in Ari, Liu, Ovistron, and Weizmann. Okay, so I've said all these things about we'd like to prove some sort of gap like this. Let me now actually state a theorem. I guess I have some space. Can people actually see this? It claims to be okay. So theorem. So there were a number of works leading up to this theorem. Initially, Kaufman-Mass studied the mixing time of lambda 2 of these random walks. Then Kaufman-Oppenheim, sorry, I guess Dinur Kaufman-Oppenheim 18, and then 11 Lau 20. And later we'll see actually even a newer version of this theorem, but for now, so let X be I'm going to use a slightly more refined variant of high-dimensional expansion. It's nothing complicated. I'm going to tell you what it is, but I'm going to write it here. Gamma 0 through gamma d minus 2 local spectral expander. This is just specifically telling you the worst expansion across I lengths. So gamma I is look across all the fixing of sets of size I. What's the worst case expansion of the underlying graph? So we just will have a bound that depends on all of the different levels of this expansion. So they proved this extremely elegant generalization of the spectral bound. That's lambda 2 of the down-up walk. Let's say it's, I guess I meant to say d-dimensional, is less than or equal to 1 minus 1 over d, which is what we expect from the cube, but there should be some decay with the gammas. So this gets multiplied by the product from I equals 0 to d minus 2 of the local spectral gaps. So in particular, if all of these are 0, which is what a 0 local spectral expander is, you indeed get 1 minus 1 over d, which resolves the Mihail-Vazirani conjecture, gives us d squared time mixing for spanning trees, matroid bases, etc. And does much, much more, because it turns out that many systems we care about, independent sets, Ising models, etc., they aren't 0 local spectral expanders. They're more like 1 over d local spectral expanders, or something like this. If I plug 1 over d into here, you'll notice this is just a constant, right? This is like roughly 1 minus 1 over d to the d, which is like e or something, or 1 over e, something. It's some constant. So this will get you a gap that's like 1 minus c over d, and will still imply quadratic mixing time for sort of fairly weak high-dimensional expanders. Okay. How am I doing on time? Now I want to actually formally go through the random walks and make sure we define things. Okay, good. I have half an hour. Okay, any questions on this before we sort of actually do things correctly with the conditional distributions and then start to prove this theorem. Yeah. Yeah, let me go over to the simplicial complex. So gamma 1, for instance, is the worst expansion on any one link, right? So if I fix 4 and I look at this local neighborhood graph, that's the link that we defined last time, the worst case spectral expansion across these one links is gamma 1. Gamma 0 is just the spectral expansion of the underlying graph of x0, x1, x2. Similarly, if this complex continued going to higher dimensions, right, gamma 2 would be the worst link expansion across fixing any edge. Gamma 3 is the worst expansion across fixing any triangle, etc. So it's just doing a level by level, finer grained version rather than saying the worst total expansion over the entire thing. And we'll see where this comes from in the proof. So you basically will do an induction level by level, and you'll pay a factor of gamma I in the level you're inducting on in the proof. Or which, there's 0. Yeah, so those are 0 local spectral expanders. So this is, you get exactly the 1 minus 1 over d bound. And this is like you can't do better than this in general because, the cube is a matroid. So 1 minus 1 over d is exactly what you hope to get. Yeah. For general system, a lot of the effort now, so there are, I think, 200 plus papers that have come out of these works. Generally, what is done now is prove the system that you care about is a high dimensional expander, like bound these parameters and just plug it into this theorem. So there's a huge amount of work and machinery that's been developed to actually prove types of Ising models and things like this are high dimensional expanders. Okay. Yeah, maybe I'll just make a quick note because we won't be able to get to it probably. Here we have this nice theorem that's generalizing lambda 2 in particular. But for the hypercube, we have a really good understanding of all the eigenvalues and all the eigenvectors, right? They're characters of f2 to the d, and we know exactly what they are, and you can use this to prove faster mixing bounds and things like this. So it's also reasonable to ask, could we get some generalization for all of the eigenvalues of the hypercube to and structure of eigenvectors and things like this to simplicial complexes? In particular, is there some sort of generalized theory of Fourier analysis of the hypercube onto these objects? The answer to this is yes. There's sort of a basic couple pages about it at the end of the lecture notes. We won't get there, but there is a theory where if you assume sort of much stronger spectral bounds, you can recover sort of the full theory of Fourier analysis on the cube. Okay, but we won't go too much into that. Okay, let's do the random walks formally then. Yeah, I'm not sure I'm going to get to agreement testing either. There's an eraser. Okay, so the way that these random walks are usually defined is through what are called the down and up operators. They're nothing more than just the adjacency matrices between levels of this complex. But I'll write it out formally for you. And let's write the space of functions. Space of functions on xk, like functions mapping xk to r. I'm going to write this as ck. So there are two averaging operators. The idea is I'm going to have some function that sits on one of the levels of these complex, and I'm going to define operators that by averaging lift the function either up a level or down a level. It's just going to correspond to the adjacency matrices. So there's the up operator, which would lift f from level 2 to level 3. There's the down operator, which would lower f from sitting on edges to vertices. And they're just defined by averaging. So if I had some function sitting across the edges here, it's like a 0, 1 valued function, I don't know. We'll do exact probabilities in a bit, but the intuition is just, what's the value of the lift of f, of U2f on 1, 2, 4? It's just the average value over its neighbors. So in this case, 1, 2 is 1, 1, 4 is 1, 2, 4 is 0, so it would be 2/3. So I'm just lifting and lowering functions by averaging their value, right? So similarly, the down operator on 1 would be the average value over 1, 2, 1, 3, and 1, 4. Okay, and this is, remember, this is exactly the action of the adjacency matrix, right? You average functions over your neighbors. This is just the bipartite adjacency matrices of this diagram. So let's do it a little more formally. So UI is an operator that maps functions on level I to functions on level I plus 1. And it's defined as UIF is equal to the expectation, sorry, I should say UIF S is the expectation over T that are a subset of S of f of T. Right, so maybe I should say S is something of size I plus 1, right? UI maps one level up, and we just average over all the guys one level below. Similarly, DI maps CI to CI minus 1, just like we said. Here we need to be a little bit more careful, because like we said, moving down is uniform. When we average down, we average uniformly, but when we average up, we average by the link probabilities. So DIF of T would be, right now I'm going to be a little bit not careful, and then I'm going to explain a sort of a nice way to think about the correct probabilities. This is the expectation over S that are contained in, sorry, S that contain T over the link distribution of T, formally, of f of S. Okay. A nice way to think about the actual probabilities that are underlying this, which are just the link probabilities we discussed before. They're just the conditional probabilities. But there's sort of a nice way to think about it. And now I want to think about, this complex is actually going up to level D. And remember how we defined all our weights and probabilities. We had a starting probability measure pi d right at the top. And then to generate each lower level distribution, I just picked a uniformly random, I drew something from pi d, and I picked a uniformly randomized set to generate pi I. So you can think about all these resulting distributions. Say xi is here. It's like pi I, pi 3, pi 2, pi 1, pi 0. I can think of these as distributed jointly over chains of faces, right? Where I first draw S up here, and then I move down one level by removing a random vertex of S, like SD goes down to SD minus 1. And each step, I just remove a uniformly random vertex from the set that I'm currently at. Right, so if this is also something somebody asked about, do I think about going multiple levels at once or one by one? It's the same, right? Because if I take 3 steps, removing a random vertex each time, it's the same thing as if I removed a random triple, right? There's no difference. So, I'll keep going. So, at the end, I've sampled this sort of chain of faces that sit in each other. And they're jointly distributed like this is sampled from pi d. The ith guy is sampled from pi I, right? Why? Because of exactly what I just said, that removing a uniformly random vertex until we get to size I is exactly the same as taking a random I subset. Okay. Now, the point is I can sort of cleanly define these operators by drawing an entire joint chain and thinking about, like if I'm, let me just draw it. It will be a little bit more clear. So instead of thinking of just sampling, at a particular level, I'm going to sample an entire chain and then look at the conditional probability given the element in the chain that I'm at. So this will be the probability. So I'll view this, full conditional probability just as I. So I'll draw S0 through SD from pi, this full joint distribution over chains. And if I have ui f of s, then this is going to be f of s I minus 1. So the I minus first guy I sampled in this distribution, conditioned on that the ith guy I sampled, sorry, did I go the wrong direction? This should be si, and this should be, no. It was right. No, let's set I plus 1. Sorry. Yes, you're right. Thank you. Maybe I should have used a different variable here, say like y or something. Right, so this is the value of uif at y is the average over lower level guides, but now I'm doing it correctly over this sort of joint distribution of chains. So this is going to make sure that I don't have to worry about sampling things from the right exact distribution. I'm just viewing everything jointly and doing everything with respect to sort of this joint distribution. So similarly, I can do the same thing below, which hopefully I don't screw up the indices of. So this should now be also S0 SD sampled from pi. And let's see, this will be, so this should be a function, sorry, di goes to I minus 1. So this is a function over I things. So this is also going to be Si. But now it's going to be conditioned on Si minus 1 is equal to t. Okay. Yeah, so I wanted to do just the expectation version first because it's a little bit simpler than looking at this series of chains. But this is really what's going on. There's this full joint distribution over every level of the complex, and the averaging operators are just saying, the value here is the average over this joint distribution, conditioned at being here of the next guy that I'll draw in this sequence. And remember, when I'm averaging down, how do I draw the next guy? It's uniformly at random. So that's why I said down was uniform. But now when I look at the conditional distribution the other direction, now it has to be drawn from this link distribution. You can do out the calculations and see that indeed, the probability, if I start here and average up, the correct probabilities I should be taking are coming from the link distribution of 2, 3 that we defined last time. Okay. So now we can formally define these random walks that we've talked about. They're just going to be the composition of these operators, right? What are these doing? They're lifting and lowering functions between levels of the complex. And this gives us basically our Markov operator. So let's now formally define the random walks. Oh, maybe one more thing I'll say. We talked also about moving multiple levels throughout the complex, right? So I can do this just by composing the up and down operators, right? I can lift a function from 1 to 3 by taking u1 and then taking u2 to lift it up, right? So it would be the composition. If I started with f, then u2, u1, f would sit up here on level 3. And it's again just to be a uniformly averaging down, but now over vertices instead of over edges. Formally, I take the average of the average, but uniformly sampling something twice again is just uniformly random over vertices. So I can also walk multiple levels in the complex via these operators. Okay, so I'm actually going to define some notation. So these composed operators, dki is going to be the thing that maps functions from k down to I just by composing the operators. So this would be dk composed down to di plus 1. That would map a function on level k down to level I. And uki will map a function from level I up to level k. So that will start at ui and go to uk minus 1. These are just the composition. If you think of these as matrices, I'm just multiplying them. This is just the composition of the operators. And now we can actually define the random walks, which are just the composition of the down and the up operators, right? This is why they're actually called the up-down or down-up walks, or maybe this is why these are called the up and down operators. I don't know, chicken or the egg. So in particular, p wedge of I is the down-up walk is just di ui minus 1. P up-down I is the flip of, well, not quite. This is ui di plus 1. And similarly, I can define the multi-level walks. Right, so let's say P down up K to I would be starting at dk and going down to I, and then lifting back to K, and P up down, K to I, sorry, a little tedious, is similarly, I to K. It similarly starts at level I, lifts up to level K, and then comes down to level I. Okay. So first of all, I claim that these walks are self-adjoint. And this is really why I went through this whole procedure, like we did last time with the weighted adjacency matrices. I'm not going to do it again. I'll explain why these walks are self-adjoint. These are self-adjoint because I defined these correctly to be adjoint operators over the pi distribution. Right? The reason I did all this stuff, and I'm sampling these from the correct distributions, is exactly so that these are adjoint operators over the correct inner product. Right? So in particular, a claim that I will not prove is that UI f g is equal to f di plus 1 g. That these are adjoint operators between all the levels of the complex, which we actually already proved because they're just the weighted adjacency matrix, and we showed that the weighted adjacency matrix is adjoint with respect to these distributions. So we already showed this. That's partially why we worked so hard last time. Okay, so now I claim it's easy to show that these guys are self-adjoint because I just flip them across the inner product, right? So if I have, so maybe first claim is this. The second claim is that I won't, write these exact things, but for any levels, et cetera, you want to take, y, you just write this out as the up and down operators, and then I would flip the u's over to be d's, and the d's would flip over to be u's, and I'd get the same walk on the other side. So these are self-adjoint operators, meaning they have a spectral decomposition, and all the machinery we've set up is going to work to analyze these things. Okay, how am I on time? 10 minutes. Okay. Great. Okay, so now I will actually write the full version of the theorem we're going to prove. And maybe I'll do the part of the proof and we'll finish it after, or we'll see where we get to. Sort of like before, once we have everything set up, the proof is actually going to be easy. The difficulty is setting everything up in the correct way. Actually, I can just modify this theorem here. So we're just going to prove a slightly more general version of this result, where I now look at d to I. So I'm going to do any length random walk. We'll just do the down operator. It turns out that because the non-zero spectrum of AB is equal to the non-zero spectrum of BA, and these walks, you'll notice, are just AB or BA, it suffices to analyze just the spectrum of the down-up walk, and you immediately get balance on the spectrum of the up-down walks. So it doesn't really matter. We're basically proving everything we would want to prove in this one statement. So this is going to be d minus I. That's the only replacement. So we're actually going to prove this by induction on I. So I'm not just making this as general as possible for no reason. This is going to be like the stronger inductive hypothesis we use to prove the theorem, and it gives us a slightly more general result on the spectral gap of every down-up walk. Okay. If there are no questions, then I will start the proof. Uh-oh. Yeah, thank you. Let's change this to J. Good call. Okay. All right, hopefully that's better. Thank you. You know what? In the proof, I'm going to use I here, and I'm going to use J here. So let's do that, actually. Okay, thanks. Anything else as I erase? Minus, and thank you. Appreciate it. D minus I. right? So the single step walk is d to d minus 1. So plugging in d minus 1 here would get 1 over d, which was what we were talking about before. So this is just a generalization of that result. And people also do study these. If you take, I steps down and back up, people call this like the I-site Glauber dynamics. This is also studied in statistical physics and these things. So having bounds on these more general walks is nice as well. Okay. All right. So goal is to bound lambda 2 of e d to I. So I want to actually, so last time we sort of bounded lambda 2, not of this random walk, but of like the underlying graph of x by looking at its Rayleigh quotient directly and splitting it up in some local to global argument to bound the local, the local Rayleigh quotients and then lifted it back. Spiritually, we're going to do sort of a similar thing, but it's actually convenient to rephrase bounding lambda 2 of this walk as bounding what I'll call variance contraction of the down operator. So let me explain this. So we're actually pretty much going to forget the walk, and we're just going to think about this down operator, which is the half of the walk, the bipartite step. Okay, so let's recall that lambda 2, by the variational characterization, is the maximum over functions f orthogonal to 1 of e down di f divided by ff. And remember that this operator is just dki uki. We'll write it like that. Instead of this, I want to analyze a different version of this expression, which is the maximum, sorry, not defined, I'm claiming they're equal, the maximum over f of the variance, sorry, this should have been d, not k. I think they're mixed up in my notes. The variance of ddk f over the variance of f. Okay, why are these things the same? Let's write f perp is equal to f minus expectation f times 1. What is the variance? It's the inner product of subtracting out the constant part doesn't matter for this operator. It's the A1's eigenvalue. So this is just dk, sorry, I. ddi f perp, ddi f perp over f perp, f perp. And now I could flip this d to be a UDI on the other side, and I would get the walk operator. So, and I've taken the perp space here, right? So this maximum over functions is the same as saying maximum over functions orthogonal to 1, because in the variance I automatically subtract out the expectation. This flips over here, right, to be UDI, and I get exactly the same expression as up here. So this is an observation of Kaufman and Mass. Actually, not from their original paper, from a later paper. It'll be convenient to think of things in terms of this variance expression instead of working with the Rayleigh quotient like we did in the trickling down theorem. Maybe just some intuition for like why would I hope that this is small, that lambda 2 is small here, that this contracts variance. I expect this because the down operator is an averaging operator, right? You can imagine that I start at some high level of the complex. I start with some function up here on D sets that's sort of spiky, that has high variance. And then I map it, all the way down. We'll say actually I mapped it all the way down to the empty set. Then it would be a constant function. It would have no variance, right? I've averaged over everything. I've completely smoothed out the function. You can imagine if instead I just average down to these 4 vertices, I haven't contracted the variance to nothing, but I've smoothed things out significantly, right? Especially if the complex is sort of connected and well-behaved. So this is sort of the intuition that's going on here, that if your complex has sort of nice local structure, that these smoothing operations will indeed act as smoothing operations, that you'll really contract the variance of your function as you lower it down the complex. Okay, that's the intuition. Okay. Am I good to go to five over, or okay? Yeah, we won't prove the theorem, but I think we'll sort of set up the parts, and then maybe we'll do a claim after. Okay, so I want to analyze this quantity. How am I going to do this? Well, pretty much the same way that I did it before. I'm going to use a local to global theorem, right? So I'm going to do this by trying to analyze the function in links and use sort of an inductive bound plus some sort of term that comes from the expansion of the underlying graph of x. It maybe makes a little more sense if I just write it out. So I need one definition. This is basically, I'm going to tell you the version of Garland's method that we're going to use for this, which is called the chain rule for variance. If you remember last time, we defined a way, if we had a function sitting on the complex, to localize it to links. Right? We had this function f of v, which sat on the link xv, and it was just defined as fv of w is equal to w. And this was how we localized in the trickling down theorem to links, right? Now we're actually going to use a slightly different, technically this is a restriction. Now we're going to use a slightly different way of localizing the function that is, I guess, often just called a localization. So given a function f in ck, right, the space of functions on level k of the complex, do I need to do, I can only do it, I can do it just on vertices. So, and a vertex. You can, of course, do this for any level, but let's just do it on vertices for simplicity. The localization of f to the link of v, so localization of f to the link of v is the function f bar v, which on a face w, so this is xv k minus 1. Instead of, when we localized over here, this would have been a function over xv k. Now we're over xv k minus 1, so it takes in one less element. And then this is just equal to f, let's actually call this maybe s, f of v union s. So I taken something of one less size that's on the link, and I just take out its value of the thing I fixed plus the element in the link. Okay, so let me now state the local to global theorem that we'll use using this notion of restriction or localization. So I guess in their paper they call this, oh, I completely forgot to credit this. This generalized version of the theorem is due to a later paper of Alev and Travis Rao, 24, I think. And this is their argument that I'm going to tell you. This argument, a version of it also appeared in Kwee Lu's thesis for just the down-up walk. It's based on the Channel-Dawn stochastic localization method, but we won't get into any of that. Okay, the chain rule for variance. It says what? So for any simplicial, d-dimensional simplicial complex, I claim we have the following sort of local to global decomposition of variance. That the variance over any level by k of f, so f is some function sitting on k sets of the complex, is equal to the expectation of the variance plus the variance of the expectation. Okay, what do I mean? The expectation over a vertex drawn from pi 1 of the local function, the variance now over the link of v, the variance over the link distribution should be k minus 1 of f localized to v plus the variance of the expectation, the variance over pi 1 of the expectation over the link of V of F restricted to V. Okay, and I just want to point out immediately that what is this expectation? This is fix V and take the expectation over everything that's sitting above it. That is exactly the down operator, right? That's how we define the down operator. So this is actually just equal to same term here plus variance over pi1, let me make sure I get this right, of dk1f. Okay, so I think we'll probably do the full proof after the break. What time is it? Okay, 3 minutes. So let me set up the two pieces then. So what have we done here? We've sort of broken this up into a local and a global term, right? Roughly speaking, what we want to do is we're trying to analyze the variance of DDI F, right? That's we're trying to prove that this contracts the variance a lot compared to the variance of the starting of F. So I'm going to immediately apply this result to it. And maybe I won't write it out now, but what this is going to get us, okay, I'll write it out now, is the expectation over V from pi1 of the variance over the link of DIF, this whole thing restricted to V, plus the variance over pi1 of DDI, wait. Sorry? This is the down operator, right? F is a function sitting on level K. I've mapped it down to this is now a function, right? This is taking the expectation over a vertex, so the value at a vertex, which is on x1. Yeah, so, okay, something that I noted in the notes but not here is that the direction of these operators is opposite, right? You move down by averaging up, you move up by averaging down. And in fact, if you look in the Markov community, they flip the definition of these. They'll call what I call the up operator the down operator, and what I call the down operator the up operator. So sorry about that. Depending on where you look in the HDX community, people flip these definitions. Because as Markov operators, they actually move in the opposite direction. D moves you up and U moves you down as a random walk. Okay, well, this should be, no, okay, this is right, sorry. DDI, DI1 of F, which is just DD1 of F. I'll correct that if it's not right at the end. But I should get a term at the end that just looks like the contraction all the way from the top to vertices of F. And now the idea is going to be as follows, that we'll finish after the break. This term, this is a global term that's sitting on the vertices of the complex X. This is something about the contraction or the behavior of this random walk on the graph underlying F. In particular, we'll show something like this is bounded, the contraction is bounded by some function of the underlying link expansion. I'll write this out as a formal claim in a bit. And this guy is inside the link. And okay, this is like not quite the right form, but we'll show that this is equivalent to just looking at the variance contraction within the link itself. But that's a one lower dimensional walk, and it can be bounded inductively, right? So we'll get this sort of inductive sequence of terms as we walk up levels of the complex. And it's some annoying, calculation to work out that it indeed shows up to this formula. So I'll write it out a little bit more formally after a break. We'll see the sort of flavor of the proof, but then I want to move on to some other things. Okay, so let's break for half an hour-ish.